All right, hello everybody. Welcome to EEE 146 Power Electronic Course, Chapter 2, Power Computations, Part 2. So here we're going to talk about Fourier series and how to quantify kind of more complex waveforms. Everything we talked about so far has been power system related stuff, S, P, Q, power factor. All this is assuming sinusoidal waveforms, very easy things to do. But sometimes in power electronics, you might get some weird waveforms that aren't your standard square wave, triangle wave, and sinusoidal. So we need a way to figure that out. Okay? And this is where Fourier series comes in. You might have heard this before, you might have seen it, but we're going to try to give you my spin on it, try to make all the complicated math break down into the whys and wheres we're doing it. That way it kind of makes a little more sense. All right. So before we really get into math, we gotta ask ourselves, what is a Fourier series? What's the whole reason why we have this? The mathematical version of a Fourier series, it's a function that has a DC component called A0, zero stands for DC, plus a family of cosine waveforms and a family of sine waveforms. And where you add them all together, and each cosine or sine waveform can be different with a different magnitude, a different frequency, and a different phase shift. And you could do both or either one of these, sines or cosines. Now, there are some rules. You can't use any sine or cosines. They have to be a harmonic of the first frequency. So for n equals 1, so you have A1, 1 W1T plus theta 1, you have to have a base frequency, and we'll say it's 60 hertz. So 60 hertz we call the fundamental frequency for power systems, so that's where you n equals 1. You could add on more sines and cosines of higher order frequency, but they have to be integer multiples. So you can have a n equals 2 where the frequency of the sine and cosines will be 120 hertz. So it's going to literally rotate twice as fast. That's called a second order harmonic. You can have a third one for 180 hertz where it'll rotate and oscillate 3 times faster. That's a third order harmonic. And you could keep on adding more cosines and sine waveforms, but they have to be multiples of that first frequency you choose. So if I choose 60, it must be 120, 180, 240, 300, 360, and so on and so on. You can't use anything else. Otherwise, this whole system collapses. Okay? Now, the fundamental frequency, you could choose what that is. We choose 60 hertz because that's what the power system is. But if you're in Europe, you'll be using 50 hertz as your fundamental frequency, or you have a very specialized circuit, you can use something else. Okay? So the big rule so far is a Fourier series is a DC component plus a bunch of sines and cosines where the frequency is a multiple of a base, in this case, 60 hertz frequency. Okay. Now, when we choose a frequency, notice that this N W1T, this is pretty much a frequency. This gets locked at 60 hertz. This one gets locked at 60 hertz for N1. For N2, these frequencies get locked at 120. But per harmonic, the coefficient in front, this could be 50 volts, 20 volts. It's just a number. It's a voltage. And the phase shift, this could be -5, 13 degrees, or whatever. These will change based on each harmonic level. And they could be all over the place. So within each harmonic level, will have its own phase shift. It will be theta 1 for the fundamental frequency for the cosine phase shift, and phi 1 for the sine phase shift. And you'll have a theta 2, a phi 2, a theta 3, phi 3, and so on and so on. So each harmonic level has its own phase shift, and it has its own magnitude as well. Okay. Now, we could kind of spread it out, and we could write this function as individual harmonics. For example, this function f1 of t could be f1 plus f2 plus f3, where f1 is a n equals 1, the fundamental frequency harmonic, and this could be 10 cosine of 377t. So 377 is 2 pi f, where f is 60 hertz. So 60 hertz is also 377 radians a second. That's where this number came from. Okay. Times t, which is the time variable because it's a function of time, plus 30 degrees. So we have a phase shift of 30 degrees right here. We got a magnitude or an amplitude of 10 for an n equals 1. Then for the second order harmonic, we'll have another cosine function, but notice the amplitude smaller, it's 5. Typically, the smaller, the higher order harmonic you go. But look at the frequency. We took 377 multiplied by 2. So this is like 700 and change, like 750 or something, if you really use a calculator to figure it out. And look at this phase shift, it's minus 10 degrees. So it's a totally different phase shift, and that's legal. We can have a third harmonic where we'll have f3 of t, where the magnitude is only 1, so it's a very small waveform, times cosine of 3 times 377. So this is like 1,000 and change, plus a positive 72 degrees. So the big trick here is you can write them per harmonic level, so you're not having this gigantic function up here. And each one will have its own unique magnitude, own unique frequency, own unique phase shift, but the frequency is always locked into this base, in this case 377, and then the multiple of that number times 2, that number times 3, 4, 5, 6, and so on. Okay. So that's all Fourier series is. It's just a collection of these sines and cosine waveforms at these harmonic level frequencies. Now, why are we even doing this? What's a benefit of putting a bunch of sines and cosines together? Well, if you're very careful in selecting the amplitude and the phase shifts and kind of play around with them, you could actually recreate any waveform that is repeatable with sines and cosines. So sines and cosines are very easy to get in a power system. You have a function generator that does it. You have rotating machinery that creates sine and cosine waveforms. It's easy to find in nature. A square wave is a little bit harder to produce, right? Naturally. But if you have some weird offset waveform, in this case, let's do square wave because it's easy. We can actually graphically draw multiple sine waves. When we add them all together, we'll get a pretty close square wave. Now, this is not perfect square wave. A perfect square wave literally goes up, is flat, goes down, and is flat and keeps doing this. Sure. But if you notice, a sine wave is kind of like a square wave, except that the edges are rounded. Okay, so we're kind of there, but we're pretty far off. But if I add a third harmonic waveform together, so I take the second waveform, add it here, what we're doing is at this point right here, we're kind of making this hump a little bit bigger than it should be, right? Because we're adding this area right here. This area gets added about right here. And then in the middle, notice we're going down a little bit, so we're losing some area here. So this is negative. So now we're actually kind of dipping down into the waveform here. And then the third one here, we're adding back in. And we're kind of doing this. Okay? Let me clean this up just a tad. So you can see by adding this n equals 3, we're actually transforming the sine wave and bending it a little bit straighter. It's not perfect, but it's kind of starting to look like a square wave, right? And if we do down here again, we'll do this, right? And as we add more harmonic levels, we could fine tune this. So this fifth one, it'll take this and kind of do this and make it even more flatter. And the more harmonics we add in, the seventh and so on, we're gonna get this waveform up here. So you can see it's a lot more flat than the sine waveform down here. And as we add more and more, it will get flatter and flatter to eventually you won't even be able to see difference. It'll be pretty much a square wave. It's not a true square wave because we're cheating a little bit. We're using a bunch of sines and cosines, but we're getting a pretty good approximation. Okay, and that's the whole idea of Fourier series is we could take any waveform, not a square waveform. I could draw something random on the board as long as it's a function and it repeats itself. We can eventually get enough sines and cosines added together to recreate that exact waveform or to approximate that waveform. Okay. And that's the whole beauty of this is I now have a tool to represent any waveform. Because so far in circuit analysis, the only type of circuit analysis you know how to do is with a DC voltage, a sine wave voltage, maybe a square wave, and if you really know what's going on, a triangle waveform. That's it, right? If I draw some random function you've never seen before, you don't know how to do sine, you don't know how to do circuit analysis. You're dead in the water. This is a catch-all where we could do Fourier analysis or use Fourier series and create that random waveform with maybe 10 or 20 sine and cosine functions. And we know how to do circuit analysis with cosine functions. We've done that all the time as AC analysis. It might be very complex in the terms that we're doing a lot of times, but at least we have a chance to solve this problem instead of just throwing a hands up and saying this is unsolvable. Okay, and that's the whole reason why I have Fourier series. It's a catch-all. So in this particular case, let's kind of straighten it out a little bit. Here we got one more. Here we got a kind of a square wave approximation. What harmonic orders did we use to create the square wave? Well, look over here. This is your n equals 1. So this is your fundamental frequency. So it starts here, and then it repeats itself right here. Okay. Same thing up here. It starts over here, repeats itself right here. So n equals 1 is the base. And then we use the third harmonic, and then a fifth and a seventh harmonic, and we added them all together to eventually get this kind of approximation. So we use the first, the third, the fifth, and the seventh. Now, how can I write this as a math function? Well, it's going to be f of t is equal to the first order harmonic. This is sine w1t. So it's right here, plus the third one. Now, this one is smaller, and it's smaller by a third. So you say 1/3 of sine 3w1t. Notice we put a 3 here because it's a third order harmonic. Then we're going to add the fifth order harmonic, and this is divided by 5, so it's even smaller. It's only 20% of the original waveform, right? And it's going to be 1/5 sine 5 times 5 w1t, so because it's 5 times faster. This is a fifth order harmonic. And the seventh order harmonic is n equals 7 is 1/7 sine 7 w1t. Okay. Now, not every harmonic is going to be 1 divided by its own harmonic level, right? It just so happens in this particular problem, it fits really nicely. But there's other times where this is not 1/7. It could be like 0.256 or some random number, okay? But I will say is as the higher order harmonic you go, so you typically have a lower magnitude because you need only a very small fine-tune adjustment to the waveform. The bulk of the waveform shaping is going to be the fundamental, the third, and maybe the fifth. First, third, and fifth will do 80% of your shaping, and then the last 7th, 9th, 11th, and so on is going to just be that very small fine-tuning. And the very small fine-tuning doesn't take a large magnitude to work with. You only need a very small amount of voltage to really polish the waveform out. Okay. Now, what I mean by polishing it is this right here. So here, we could make a sawtooth waveform with sines and cosines. So we take the fundamental 60, let's take a random sine wave right here, right? Pure sine wave, there's no sawtooth involved at all. If we're going to add a second order harmonic onto the fundamental, notice that the sine wave kind of ends prematurely and it stays at the bottom, does nothing, and then it shoots to the bottom and then shoots back up. So you see it gets a little lopsided, right? But that's kind of what we want. To make a sawtooth waveform, we need a lopsided waveform to begin with. So by adding a second order harmonic, we're kind of shaping that waveform. So we're kind of getting to a sawtooth, but we're pretty far off. This still looks like a sine wave to me. Let's add a third order harmonic. We could kind of change the magnitude, shift it a little bit, and now we're kind of making these bumps smoother. So you can see we're going up, and we're having these kind of little jagged bumps. We're going back down, going back up, jagged bumps back down. But you can see we're kind of making a sawtooth. It's kind of into shape now. It's still rough, though. Add a fourth order harmonic. It's getting smoother, a fifth one, and all the way to the 20th level. So we had 20 families of cosines and sines added in. And now this is our end result, which this is a pretty good approximation of a sawtooth waveform. It's not 100% perfect. There is still a little bit of noise, but it's so small, you might as well call this a real sawtooth waveform. Okay. And this is how Fourier series can take sines and cosines, which we could easily get, and create a sawtooth waveform, which is a lot harder to make. Okay. What order harmonics did we use to create the sawtooth waveform? We went first, second, third, fourth, fifth, all the way up to the 20th harmonic. You can even go more if you want. But at this point, this is polished enough that I'm okay with stopping at the 20th order. Okay. So this is seeing the Fourier series in action. Okay. Now, we have a way to find a random signal, a random voltage source. We don't know the waveform. We could create a family of sines and cosines to represent it easily. Okay. Now the next question is we have this random signal defined in a circuit. It's powering up a resistor, capacitors, inductors, and the rest of the system. How can we do circuit analysis? Because that's a second step. First step, identify the waveform, quantify it mathematically, and now let's do actual circuit analysis to figure out power, voltage, current of the system. That way we could design a circuit to work with this random waveform that we found. Okay. And I guess I should say, when I say random waveform, where would you find something like this? Well, a perfect example will be, what if you, in your wall socket, you expected 60 hertz and the sinusoidal waveform is 60 hertz? It should be. But if you're near a refinery or a large plant that's kind of not that great, it's old, it might distort the voltage and you might get a distorted signal. So instead of being a sine wave, you might get a really mucked up waveform, right? And you don't know what to do with that. That could burn up your equipment. Your refrigerator might be prematurely dying every 3 months because it's this distorted random waveform pattern. And that's because a refinery next door to you is messing up the power system and you're the victim of this, or you're the collateral damage of their poor decisions on equipment choice and how they operate. Okay. How can we quantify how much power you're losing, what the voltage and current is to your house to know why your equipment's burning up? Why are you taking damage, right? That's where we're going to take that random waveform with an oscilloscope. We could do a Fourier transformation to find those sines and cosines, and then we can enter circuit analysis to get some hard numbers to then go to the refinery and say, you're screwing me over with this. Here's my proof. You need to replace my refrigerator and that type of stuff. Okay. That's kind of the logic of why we need this. Okay. So let's talk about circuit analysis. For any nonlinear voltage and current. So remember, what does nonlinear mean? It means every time I hear nonlinear, it means not nice. It means hard. Okay. It's a weird shape. It's noisy signals. It's something I don't normally see. I need help to analyze this weird one-off thing. Okay, so that's what nonlinear voltage and current looks like to me. We can use Fourier series to represent this voltage and current. Here are the rules for circuit analysis. So the first thing is, any periodic waveform, as long as there's a pattern, we can represent it with that Fourier series with harmonics between n equals 1 to 20 or however long you want to go. Sometimes you go from 1 to 49. 49 is about the limit I've seen, or 51. Most meters and most devices won't go past that because it's a waste of time. Okay. So once we take a meter or oscilloscope, we plug it in, we read it, it's going to do its Fourier transformation and spit out all our harmonic levels for us. Okay. Now we have each harmonic level. We have all of the sines and cosines we need. We could then look at a circuit and do simple circuit analysis by looking at the circuit per harmonic. Okay. So each harmonic level can be treated as a separate circuit running at a higher frequency. So instead of having a circuit with 20 voltage sources for 20 different harmonics, because you would draw with 20 different sources. It's very similar to superposition, where you could delete all the sources and just look at one at a time. So we're going to look at the 60 hertz signal and ignore all the other voltage sources. We're going to look at 120 hertz signal, ignore all the rest, because it's easy to do circuit analysis with one source. It's hard to do with 20 all at once, right? So this is the idea, is we're repeating a very simple circuit technique we've always used in engineering 17, like node analysis or Ohm's law. We just got to do it per harmonic level. And if we have 10 harmonic levels, we got to do it 10 times, right? But I'd rather do 10 things at a very easy pace than one thing at a near impossible pace, right? Because at least I know I could do this simple thing correctly, okay? So that's the second rule, is go per harmonic, do your circuit analysis. Okay. Once you have the answer in each harmonic level, you could then combine them, recombine them into a resulting Fourier series for your total voltage, your total current, right? You could ask anything. Each current voltage will have an answer for all the different harmonic circuit analysis per harmonic. So you might have impedance for n equals 1, impedance for n equals 2, n equals 3, n equals 4, and n equals 5. You can have current for n equals 1, 2, 3, 4, 5. You can have voltage for n equals 1, 2, 3, 4, 5. You can even have power for n equals 1, 2, 3, 4, 5. Okay? Now, once you have all levels of harmonic analysis done or all levels of circuit analysis done per harmonic, you can recombine them to find a total RMS value for the current or the voltage, right? So then you could combine RMS voltage and current per harmonic back into one gigantic, this is my whole circuit, okay? So you can take every single harmonic level, in this case the current, take I0, 0 is a DC, square it plus I1 square for the first fundamental harmonic circuit, find the current for n equals 2 for the second order harmonic circuit. You can do 3, 4, 5, 6, 7, all the way to 49 if you have that many. Add them all in squares and take the square root of them. This is called the sum of squares. And that's going to be your total RMS current for the entire circuit with that really chopped up waveform. Okay. More formal way to write this is I RMS can equal the square root of the summation between 0 to 49, where you take each one and you square them and add them together first. So square each individual harmonic current, add them all, and then square root the thing at the end. Okay. This is how you add harmonic current together. You can't just literally add 1, 2, 3, 4, 5, 6 together arithmetically. That's going to give you really, really wrong answers. Okay. For power, though, it's a little simpler. To find the total power of all harmonic levels, combine them to this is my real life circuit, is you take the total power and P0, you take the power per harmonic level for P0 plus P1 plus P2 plus all the way to plus P49, add them all together, and that's your total power. So it's a basic summation. Okay. Now I want to take a caveat here. We're talking about doing harmonic analysis per level. You can, but you have to remember, harmonic analysis, this is a mathematical model. It's not what's actually happening in real life. In real life, that wall socket is giving you the messed up waveform, and the messed up waveform is creating a lot of power, burning up your fridge. Okay? The wall socket is not giving you 20 different signals, and your refrigerator is not 20 different circuits. It's only one circuit. But we're mathematically taking a complex waveform, splitting it up, solving it per harmonic, and then recombining it. This is just a mathematical model, but the end result, this power total, this RMS total, this is a physical quantity in your device causing problems or inducing power. That's physically happening. Okay, so just remember this whole Fourier analysis, this harmonic analysis, we're taking real life things, splitting up into 20 mathematical models, doing our circuit analysis and mathematical models, recombining it, and then the end result is a physical quantity we have again. Okay. A lot of people take a mistake and think that there actually is 49 different. Like some people think your refrigerator literally has 49 shelves of different circuits, right? And then each harmonic goes to each shelf that day to use. No, that's not how that works, right? There's literally only one circuit. Okay. So just want to make sure we're not getting too deep into the math and thinking the math is real, right? Math is just a model. And anytime you hear model, just think a model is a fake version of a real life thing. Okay. Modeling is just a shortcut for us to figure out what's going to happen in the future. Okay. So the last one optional part we could do is once we have the total power, the total RMS current, those are real life quantities, we could figure out a ratio called total harmonic distortion. And some places use this as a metric to see how harmonic rich our environment is. So let's say we have a voltage coming out of a wall socket, right? The higher the total harmonic distortion, the dirtier the source is. The more harmonic content, the more noise, the more damage you could do. So a high THD is bad. You don't want this. Lower THD means you have a cleaner waveform, it's smoother, and that's what we want. Okay? So you could figure out THD, total harmonic distortion, by taking all your higher order harmonic levels, when n equals 2 all the way to 49, finding the sum of squares of all those and divide by the original fundamental waveform, I1. And this ratio will say how clean your system is or how close you are to the I1 waveform, because I1 is a sine wave. Okay, so if our messed up waveform looks very close to a sine waveform, when we do our harmonic analysis, this THD is going to be very low. Right, but if we have a very chopped up waveform that's very spiky and doesn't look anything like a sine waveform, then our THD is going to be very high. Okay, but that also means it's a lot harder to do the computation for that circuit and to recreate it. And in general, I'm just telling you, THD is a bad thing. We want to keep this as low as possible. When you look at converters, when you're sizing equipment, you'll probably see total harmonic distortion. You can say, hey, this thing should be less than 15% or 25% or something. You don't want it to be too high. Okay, so just don't be surprised you ever see THD, and now you kind of have a rough idea of what it means. Okay. So I threw a lot of math at you. Let's do a problem. This is going to be a very long arching problem for the rest of the class period. I'm going to start it. You're going to take a little break in a second for you to keep going, and we'll come back and finish it. But you need to see from start to finish, how does a circuit analysis work for a Fourier series. So we have a non-sinusoidal periodic voltage. We don't know what the waveform looks like, but it's all crapped up. This voltage can be represented by V of t equal 10, which is a DC offset, 10 plus 20 cosine of 2 pi 60 t minus 25 degrees. So immediately I know this is my n equals 1. This is the lowest order frequency. So this is my first harmonic. Plus 30 cosine of 4 pi 60 t. So you can see when we went from 2 to 4, this is twice as high. So this is my second order harmonic. Okay. So we have a voltage that can be modeled as 3 separate sources. And then this voltage is connected to a load of 5 ohm resistor and a 15 millihenry inductor. And this is how we could draw the circuit. We draw the load, and then we draw 3 voltage sources in series, and each voltage source represents one of these harmonics. You have the DC component here, you got n equals 1 right here, and you got n equals 2 right here. Okay. Now some of you might be confused why when I say n equals 1, why is there 2 pi 60? They just wrote 2 pi 60 because this is a 60 hertz signal, and when you go to radians per second, you remember omega 1 is equal to 2 pi f. And f is 60, so they got lazy. I think they should have wrote 377, but they didn't. They wrote 2 pi 60. Okay, but this is our fundamental frequency right here. Now, the first step we need to do is let's look at the circuit per harmonic level. How many harmonic levels are there? There's 3. We got 0 right here. We got 0 right here. We got 1 right here, and we got 2 right here. I'm going to do 0 right now. So n equals 0 is a DC offset. So when I imagine this, what I do is I just straight up ignore and cross out anything that's not 0. So this source right here does not exist. We're only looking at the n equals 0. That's this green one right here. This source does not exist right now. So we're going to have a voltage right here. And then what about the load right here? Well, remember it's DC. What is impedance of an inductor at DC level, at steady state? Remember, DC means frequency equals 0. So if my frequency is J n omega L, and I put omega as 0, or n equals 0, then obviously I'm going to get 0. It's going to be nothing. So the inductor doesn't do anything. All we're left with is a 5 ohm resistor. So I know my Z0 is 5 ohms. So we solved that first, the n equals 0 DC component. It's just 10 volt source and a 5 ohm resistor. Okay, so that's for n equals 0. Let's reset. So reset. All right. Now let's do n equals 1. This is a fundamental harmonic. So first off, let's look at our voltage sources. Which one we're going to use? We're not using 0 anymore, so we're going to delete that. We're going to look at 1 right here, and we're not going to look at 2. We're going to delete that. Okay, so we'll only look at this middle one here. So what's my voltage source? Well, that's already given to us. It's right here. So we just got to look at 20 cosine of 2 pi 60 t minus 25 degrees. This is our voltage for n equals 1, the fundamental frequency. I can extrapolate this into phasor form and just call this 20 angle negative 25 degrees, right? 20 is amplitude here, negative 25 degrees is a phase shift here. This is not RMS, this is just pure amplitude right now. Okay. Now, what about my impedance? This is going to change a little bit because now we have frequency. Impedance of an inductor is typically J times omega L. But remember, omega can change because we have different order harmonics. So it's not just JWL anymore, it's JNWL, where N is that harmonic order. The W right here, this is always going to be 2 pi 60. That's never going to change. But this N will change. Previous up here is 0, now it's 1. So the impedance of my inductor, I'm going to write JX1 just to signify fundamental harmonic impedance, is J1 for n equals 1 times 2 pi 60, that's our base frequency, times 50 milli, because it's a 50 millihenry inductor. We're going to number crunch this all together, and we're going to get J 5.65 ohms. So for the n equals 1 frequency of 60 hertz, our circuit will have a voltage of 20 angle negative 25 degrees, and our total impedance of the load is now 5 plus J 5.65 ohms. So it's different than n equals 0, obviously. Okay? And all you got to do is just repeat this process over and over again for every harmonic system you have to find your circuit. Okay? Now, this is where I'm going to let you do the next step. I did 0, I did 1. We're going to take a 15-minute break with this exercise. I want you to figure out the voltage and the impedance for n equals 2. So go back over here, do the same thing we did here, except n equals 2. Okay, figure out which voltage sources we need, which ones we don't. Figure out your actual voltage, figure out your impedance, Jx of 2, and we'll come back and we'll check your answers, and we're going to use that to keep building up on this problem. Because this is only the first 1 or 2 steps. We're just building a circuit. We haven't even done circuit analysis yet. Okay, so let's come back in 15 minutes, figure out what your V2 is and your Jx of 2 and your Z2 impedances are, and we'll keep going from there. Okay, so good luck. See you in a little bit. All right, hello, welcome back to EEE 146, Chapter 2, Power Computations Part 2. Back from our 15-minute break, so let's kind of see how we could do this n-2 second order harmonic circuit analysis. So remember, frequency is 60 hertz, so our fundamental is 2 pi 60. So second order harmonic means it's twice that, so 2 omega 1 is equal to 2 times 2 pi 60, or 4. Come up here, we have this one right here, 30 cosine of 4 pi 60 t plus 20 degrees. So you know this is the voltage source. Come to our circuit. The DC voltage here, we're not using the first order, the n equals 1 first order voltage, we're not using as well. We're only using the second one, right? So here V2 is now 30 angle plus 20 degrees. So notice I put 2 here to signify this is a second order harmonic voltage. The load, you'll have the inductor, which is 15 millihenries. That still is here, but the frequency changes the impedance value. So Jx of 2 is now equal to Jn omega L. And Jn is 2, omega 1 is 2 pi 60, and L is 15 milli. So crunch it all together is going to be 11.3. Technically, this should probably have a J right here. Like so. Okay. All right. So our total impedance is going to be Z2 is equal to 5 plus J 11.3 ohms. So notice that the impedance of the inductor gets bigger as our harmonic orders get higher, but the resistance stays the same. That's because resistance, it does not change based on the frequency. Only capacitors and inductors change based on frequency. So we had the framework built for each harmonic level. Now we're going to start doing our circuit analysis. So we'll go literally redraw the circuit per harmonic level and do all of our calculations. So the first one is going to be n equals 0, where we have our DC offset. So we're going to have a voltage source, and this is going to be V0 of 10 volts. We're going to have current flowing through it. We're going to have resistance of 5 ohms. We're going to have inductors of 15 milliamperes. But for this particular case, the inductor is 0 ohms, so I just wrote 0 to remind myself. So let's just find the current flowing through. This current is going to be I0 for the DC offset current. So just using basic Ohm's law, I equals V over Z, where we're going to have 10 volts over 5 ohms, so we're going to have 2 amps. So the current for the 0 order harmonic is 2 amps flowing in this circuit. Power for the circuit is going to be P equals V times I, because it's DC, it's very easy. We got 20 volts coming out the source. We got 2 amps coming out the source, so the power for n equals 0 is 20 watts. So you can say we completed a circuit analysis for the 0 order harmonic right here. So we kind of put that aside and we're done. It's going to repeat the same process for n equals 1. It's just going to be a little more complicated because now we have vectors and phasors to deal with. But the same logic stays. We have a voltage source. This is V1. We have an impedance of 5 ohm resistor and 15 millihenries. But now this inductor is actual impedance is J 5.65 ohms. And now it's a simple loop, so we just use Ohm's law. We're going to have I1 is equal to V1 over Z1, where we know V1 is 20 angle negative 25 degrees. We can get that from right here. We know the impedance is 5 plus J 5.65 ohms. We figured it out previously. Number crunch check is going to be 2.65 angle negative 73 degrees amps. And this is a current. Power is going to be P1 is equal to the VRMS times the IRMS times the cosine and angle between the voltage and the current of the first order harmonic. Okay. Now, these numbers, because they're coming from V of t, where it's just straight off the cosine, when you convert them to RMS, so both the voltage and the current needs to get divided by square root of 2. So we take V1 divided by square root of 2 times I1 divided by square root of 2 and their cosine. So to number crunches here, V1 is 20. We got that there. I is 2.65 divided by square root of 2 twice. Multiply these together, you just have a 2. Cosine of the angle between the first voltage is negative 25 degrees right here. And the angle for the current is negative 73 degrees. You got it right here because this is a current voltage. The phase shift for the current of the first order harmonic. So 2 negatives flips over to the positive. So we have this number. We number crunches in the calculator. For the fundamental harmonic, we're pushing 17.7 watts to the load. So you see, per harmonic is going to be vastly different. N equals 0 had 20 watts. P1, we have 17.7 watts. Okay, now let's do N equals 2. We're going to use the numbers you guys just got. So same logic here. We have a voltage source. This voltage source is now V2. We have the same current loop. Notice that the circuit is the same for every single one of them. We're just changing which numbers we're using. Okay, same 5 ohm resistor, the inductor 15 millihenry is now J 11.3 ohms. Okay, remember this is higher because it was a second order harmonic. So I2 is going to be equal to V2 over Z2, where V2 is now 30 plus 20 degrees. You got that right here. Divide by 5 plus J 11.3, which we got from your exercise we just did. Okay. Then we crunch this. Our current is going to be 2.43 amps with an angle of negative 46 degrees for I2. Now power, we're going to have to calculate P2. Same thing as before, is V2 times I2, but they need to be in RMS. We're given amplitudes right here, like this 30 is part of its cosine. So we're going to divide by square root of 2 for both of these. Then we'll multiply by the cosine of the phase shift between the voltage and current of the second order harmonic. That's why I have to write V2 and I2, because denote we're on the second order harmonic circuit. Okay, in this particular case, V2 is 30 from right here. I2 is 2.43 from right here. We divide by 2 because the 2 square root of 2 is double up. Cosine of the angle between the voltage. Second order voltage, phase shift is 20 degrees right here, so we put a 20. Second order phase shift, second harmonic phase shift of the current is right here, negative 46 degrees. So we have a minus a negative 46, so we double up to a positive 46 degrees. And we number crunch this as well. So multiplying this together, we're going to get P2 equal 14.8 watts. So now we have I2 and P2. These are the two unknowns. And now we have the circuit solved for n equals 2. So we did n equals 0, n equals 1, n equals 2. Notice we did 3 separate circuits. We did 3 times the amount of work, but to be honest, this is not hard work. This is just arithmetic with phasors, and it's very simple one loop equation with Ohm's law, right? It's not that much headache to do this. And if you really want to do this on a large scale, let's say you have n equals 49, you're better off writing an Excel sheet to pre-program all this, where all you do is plug in V2 and maybe you could honestly you could program everything where all you enter is R, L, and V for V2, and V1 and V0. Everything else you can hard program in Microsoft Excel, and you'll just spit out all 20 numbers all at once. Okay, that's what I do when I do these type of problems. I don't do this on paper every single time. We're doing this right here to show you, but realistically, you should program this in Microsoft Excel or some other more sophisticated programming language to make your life a lot easier. Okay. So now we have the voltage and current per harmonic and the power per harmonic. We're not done yet. We need to combine it all back to the main circuit, because remember the original circuit had all this combined into one loop. So the total power for this particular problem is going to be all the separate harmonic powers added up. P0 plus P1 plus P2. We know is 20 plus 17.7 plus 14.2. Our total power is 52.5 watts. So this kind of non-sinusoidal voltage source, whatever this is doing, it's in the end of the day, it's given 52.5 watts into the circuit. There's no other way you could figure this out without using Fourier series. This has been way too hard. Okay. Now, we could calculate the current RMS for the whole circuit and double check to make sure the power is correct. Well, we could, first thing, let's do IRMS. So the current for the entire circuit, not per harmonic, all harmonics combined together, is a sum of squares. So you take the RMS of each individual component per harmonic, square them, add them all together, and then square root them. Okay? And this is where you got to really watch out to make sure you're in RMS quantities. This is where people can make mistakes. The I0 is DC, is 2. This is already in RMS quantities. If you remember from earlier this week, the RMS quantity of a straight DC component is the DC component itself. That's what RMS means, is a DC equivalent. If you're already DC, nothing changes. So DC components do not divide by square root of 2, it just stays the same. Well, you got to square it and then add the current for n equals 1, which is a sinusoidal waveform of the fundamental frequency. But because it's sinusoidal, you need to divide by square root of 2. Remember, IRMS is equal to I amplitude divided by square root of 2 for all sinusoidal waveforms. And for your series, these are all sinusoidal waveforms. So anything past I0, you're going to have to divide by square root of 2 to get RMS values from the amplitude. Okay, so 2.65 divided by square root of 2, square that, plus 2.43 divided by square root of 2 and square that. Then you add them all together and square root the whole thing, your total current is going to be 3.24 amps. Okay, so your whole circuit combined, the end of the day, the current that the current meter is going to read is 3.24 amps. That's physically what's going on in the circuit. Okay, they could double check the power. The power to the load. Let's go back to the circuit real quick. This circuit right here, where does power get dissipated? We know power from the source. We calculated this. What about the load side? Power is only ever dissipated off a resistor. Power is never dissipated off an inductor. Reactive power is dissipated off an inductor. But for regular power, it's only the 5 ohm resistor. So all we need to do is figure out how much current's flowing through it and use the resistor and current to figure out total power. And we can do that easily. The total power is going to be I squared of the total RMS times the resistance. Remember, P equals I squared R. That's a very common equation. Let's number crunch this. 3.24 is the total current. You square that times 5. Our power is 52.3 watts. Very close to these two. There's probably a small rounding error because I chopped off numbers here or here. But overall, this is close enough that they're equivalent. This is a nice way to double check to make sure your work's okay. All right. So that is for your series from start to finish, right? It's very long-winded tool, but it at least gives you an option to do something. Okay? And I'll tell you this from my personal experience. I've studied this. I'm actually pretty good at this. If you understand all this and you can use it in a practical sense when you go work, everybody's going to be amazed because most people in the world don't know this and they don't know how to use it past just mathematical junk, right? So if you could really get into this, you're going to be one of 10,000 engineers in the world that really can use this. People are really looked up to you. You'll get all the specialized project. You're going to be that specialized consultant, and money's probably going to start flowing your way because you know how to solve the unsolvables. Okay, anybody can solve an easy problem. We don't pay money for you to solve simple things. We pay high dollar for the people who solve the impossible and make the impossible possible, right? And this is one very good tool you could use to do that at the most complex level. Okay. So let's do a summary of Fourier analysis, Fourier series and circuit analysis, harmonic analysis, all that good stuff. How can we represent complex waveforms in circuit analysis? We can take several sinusoidal waveforms of higher order harmonics, add them together to recreate any waveform out there. Okay. What harmonic waveforms of the fundamental 60 hertz signals do we use? When a waveform with a frequency of 60 hertz is a base, we use multiples of 60 hertz. So second order harmonics would be 120, the third is 180, the fourth is 240, the fifth is 300. It's going to be always a multiple of 60. Just keep on adding extra 60 every time you go up a harmonic. Okay. What are steps to set up a circuit for harmonic analysis itself? We just did that. Number one, analyze the circuit separate for each harmonic present in the source. Look at your source volt, look at the source waveform, do your Fourier transform, figure out what level of harmonics we're using. Maybe we're using 1, 2, 3, 4, 5. You're going to have to do a circuit analysis and get a separate sheet of paper for n equals 1, 2, 3, 4, 5. Maybe you're doing 1, 3, 5, 7. Do a separate sheet for 1, 3, 5, 7. Okay, you're going to do a separate problem for each harmonic level. Figure out your voltages, your currents, and powers, everything you need. And then number two, to find the total power of the whole circuit, add up each harmonic power. So add up each one from n equals 0 to as high as you go, 49, infinity, however you want. So you just add them all together. For the RMS current, you got to take each one and add them as sum of squares. So honestly, it's the same thing for voltage as well. I said current, but if you want the RMS voltage for the whole circuit, it's going to be each individual one added in squares. So take I0 square it, add it to I1 square plus I2 square plus I3 square. That's what the summation means. Add each one, square them and add each one together, and then square root everything off, the whole thing at once. And that's your final answer. Just don't forget that all of these voltage and currents right here, they have to be RMS current for each harmonic. So if you're given amplitude, you got to do that divide by square root of 2. If you already have RMS current per harmonic, then don't divide by square root of 2 again, because now you're screwing you're getting wrong numbers. Okay, so you got to know when to divide by square root of 2 and when not to. Okay. So that's all I have for your series and circuit analysis. Hopefully you got this super complicated thing, maybe broke it down to it makes a little more sense of why we're using it. You at least know the steps on how to use it, and you can maybe sometime in the future it might come in handy. That's the whole idea. Okay. In terms of power electronics, we're gonna have some funky waveforms. So a lot of times it's good to do the Fourier analysis to see what's the total power and what's the total current from this funky waveform we got from our power electronic converters. And then maybe get some THD to see if it's good or bad, and then do some analysis. And if it's good, it's a good product. If it's bad, we got to go back to the drawing board and redo it. Okay. So that's all I have for today. Hope you guys have a good rest, and gals have a good rest of the week, and we'll catch you next week for the next set. So see you around.